we have seen how the critical depth and the associated concept of critical flow allow to classify flows into subcritical or supercritical. We have also seen that the critical slope indicates the limit between mild and steep slopes, and that this limit is not only determined by the actual geometrical slope, but also by the flow conditions. The table here summarizes the different possible situations. For example, we know that for a horizontal channel, the normal depth HU tends to infinity, while the critical depth can be calculated. Obviously, for an adverse slope that is S0 smaller than 0, there is no normal depth, while the critical depth can still be calculated. In fact, the critical depth can be calculated for any possible slope. Then, for positive bed slopes, we have the mild slope, the steep slope, and the critical slope with finite values of both HU and HC. The uniform flow is defined as an equilibrium flow, for which the friction slope SF, that is the slope of the energy grade line, is equal to the bed slope. When discussing the uniform flow, we have seen that if the water depth is larger than HU, the friction slope SF is smaller than S0. And if H is smaller than HU, it is the opposite. SF is larger than S0. Now we will combine all these concepts to analyze the evolution of the specific energy. Let us consider a portion of gradually varied flow between section 1 and section 2, distant of delta S. The definition of the specific energy is recalled here, where the second term here on the right-hand side represents the kinetic energy here. We have thus here E1, specific energy in section 1, and E2, the specific energy in section 2. From this reference level here, we can determine the difference in bed elevation between the two sections, that is S0 delta S. And from the energy level in section 1 and 2, we can determine the head loss SF delta S. We can thus write the energy balance between the two sections like this, and considering the limit when delta S approaches 0, we finally have this differential equation for the evolution of the specific energy. From there, we can analyze different possible cases. As we have seen, in the case of adverse slope, there is no uniform flow possible. We can only define the critical depth HC with the critical flow C. The bed slope S0 is negative and thus always smaller than SF. Therefore, dEds can only be negative, which means that the specific energy can only decrease along the flow from upstream to downstream. So, if we consider a starting point here below HC, we see that if the specific energy decreases, the flow depth will increase progressively until reaching the critical depth at point C. In the same way, we can consider a starting point above HC. In this case, a decrease of the specific energy will correspond to a decrease in the water depth until reaching the critical depth. The case of a horizontal channel is very similar to the adverse slope. There is no uniform flow possible, and as SF can only be smaller than S0, the specific energy will always decrease. This leads to the two same cases as before. A flow below HC will see its depth increase until HC, while a flow above HC will see its depth decrease until HC. In the case of a mild slope, we have more possibilities. Here, the normal depths exist, and we have the uniform flow represented here by u, and we see that HU is larger than HC. If we consider a point below HC here, and thus below the uniform depth HU, SF will be larger than S0, and the specific energy will decrease. This will correspond to an increase of the water depth until reaching HC. If we consider a point above HC as here, but still below HU, SF will still be larger than S0, and the specific energy will also decrease. But now this decrease in specific energy corresponds to a decrease in the water depth until reaching HC. In the case of a uniform flow, SF is equal to S0, which means that the specific energy remains constant, because we have here S0 equal to SF. So the flow depth will always remain constant and equal to the normal depth. This shows again that the uniform flow is a stable or an equilibrium situation. Finally, if the water depth is larger than HU, the friction slope SF will be smaller than S0 and the specific energy will increase. Accordingly, the water depth will also increase. This increase appears to be without limit until infinity, but in the reality, as we will see later, boundary conditions in the flow will play a role and possibly control this increase. Let us now consider the case of the critical slope. Here, HU is equal to HC. For a point below HU, the specific energy will decrease, as here, with an increase of the water depth until HC. And for a point above HU, the specific energy will also increase, as well as the flow depth. Finally, we have the case of steep slopes. For H below HU, the specific energy will decrease and the water depth will increase until reaching the uniform depth. For a depth between HU and HC, as we are above HU, the specific energy will increase and the flow depth will decrease until reaching HU. And for a depth larger than HC, thus also larger than HU, the specific energy will increase, but this time the water depth will also increase. So, in this lesson, using the classifications of the flow presented before, we could analyze the evolution of the specific energy under different conditions, and accordingly the evolution of the water depth. We will see in the next lesson that each type of evolution corresponds to a specific water profile. So, see you in the next lesson.